Hello everyone, my name is Fernando Campo. I am a PhD student at the Laboratory of Air Quality Control at the Federal University of Santa Catarina in the city of Florianópolis, Brazil. Today, I will present some preliminary results that my colleagues and I have achieved in the last months regarding the development of low-cost air quality monitoring sensors. During the last decade, air quality monitoring has experienced a paradigm shift in the way data are collected. This was stated in 2013 by Emily Snyder and contributors in a paper called The Changing Paradigm of Air Pollution Monitoring. According to the authors, the recent advances in electrical engineering, quote, provide opportunities to enhance a range of existing air pollution monitoring capabilities and perhaps provide avenues to new air monitoring applications. End of quote. These newly emerged monitors are commonly known as low-cost air quality sensors, as a direct reference to the relatively lower cost of the hardware component needed to make a measurement, compared to certified methods. However, such devices have other valuable defining features like smaller dimensions, lower weight, lower power consumption, and easiness of use that better differentiate them from the traditional monitoring methods. This set of features has opened a new and broader spectrum of air quality monitoring applications, and these instruments present themselves as a promising alternative for monitoring air pollution, especially for developing countries. At the Laboratory of Air Quality Control, we have developed two low-cost measuring prototypes, one for fixed measurements and another for mobile monitoring. As shown in the figures, both nodes use an Arduino Mega microcontroller platform, a micro SD card module for data storage, and an ESP8266 microcontroller for Wi-Fi communication. The mobile node also includes a GPS module for geolocation and timing. Both devices feature 4 screen-printed electrochemical gas sensors from Specky Sensors that connect to a WART port over an RS-485 bus. The sensors are sensitive to the pollutants carbon monoxide, nitrogen dioxide, ozone, and sulfur dioxide. Besides these 4 sensors, the fixed or static node includes 5 alpha-sense electrochemical transducers, also sensitive to the gases that I previously mentioned, as well as hydrogen sulfide. We deployed the static node at a meteorological measuring site within the university campus, close to a street with a regular and frequent flow of heavy vehicles, more specifically, buses for public transport. It is worth mentioning that the period of data gathering corresponds to the coronavirus outbreak in Brazil. Thus, public transport in our city was considerably reduced and even banned for some periods. Anthropogenic activity decreased in general. The static node collected air pollution measurements in 2 periods of approximately 3 months each. The first one spanned from March 14 to May 26. During this initial period, we used a solar panel as a power source and a 12-volt battery for power storage. During the second period, July 14 to September 3rd, we connected the node directly to the power network. For mobile measurements, we used our prototype and the Sniffer 4D version 1 from Shenzhen Soarability Corporation, which uses alpha-sense electrochemical sensors. Air quality readings were taken from 3 streets with median traffic, as well as residential areas, from Monday to Sunday during a period of 4 weeks. We choose 3 different times of the day that better capture the daily traffic pattern. The reason for performing these measurements was to obtain preliminary results on the performance of the instruments. We were seeking to answer the following questions. Are the responses of sensors from different manufacturers correlated for the same pollutant? Do the sensors detect daily and weekly variations on traffic patterns? Do sensors' responses correspond to the level of pollution expected at specific locations? And finally, what is the effect of environmental conditions like temperature or relative humidity on sensor response? So, let's start with a fixed node at the university campus. For the rest of this presentation, I will focus only on the responses for carbon monoxide on March 14 to May the 26th, when we considered that the data collected was more useful to our purposes. The reason for this choice is that during the second campaign of measurements, as shown in the pictures, the alpha-sense sensors suffered from repeated baseline drift and spikes, related, apparently, to peak values on the concentration captured by the SPECI sensor. We don't know the reason for this effect. It could have been caused by energy fluctuations or by actual high pollution events. Since these situations are at more questions than responses, we did not consider this data in our analysis. Back to the period of interest, the figures show the responses of the SPECI sensor for carbon monoxide, the DGS-CO, and its homologous from AlphaSense, the CO-B4. As you can see from the last figure, the absolute level of response of the SPECI sensor was between 6 to 8 times higher than AlphaSense. The following figure, to the right, shows the sensor outputs normalized for better visualization. As you can see, at certain periods, the responses seem to be positively correlated. But in other intervals, the opposite is observed. This leads us to our first question. Are the outputs of the sensors correlated? As shown in the right figure, the correlation between the responses of the sensors was low, with Spearman's and Kendall's correlation coefficients very close to 0. The next figure, on the left, illustrates the daily behavior of the relative humidity and the readings from the carbon monoxide sensors. The data was hourly aggregated. In those graphs, the similarity between the relative humidity and the SPECI sensor is visible. The scatter plot on the upper right figure confirms their correlation, which was 0.5 according to Spearman coefficient and 0.4 according to Kendall's. The correlation between the output from AlphaSense CO-B4 was low, approximately 0.1 for both Kendall and Spearman. Its daily pattern, on the other hand, reveals an increase in the response during the hours of more intense traffic activity, from 16 hours to 18 hours. Once this pattern was detected, we removed the daily seasonal component from the responses to check for correlation in the trends of the responses. Again, both CO sensors were found poorly correlated. The figure on the right shows the weekly behavior of the sensors. As can be observed, the SPECI sensor output remained with little variation throughout the week. In contrast, the AlphaSense sensor recorded graded variation in the median concentration, with a higher value on Wednesdays and lower on Saturdays. In general, the median concentration values from AlphaSense and its variability were lower on weekends than on the rest of the week. The trends of the relative humidity and the response of the SPECI DGS-CO sensor also showed low correlation. Spearman's and Kendall's coefficients were approximately minus 0.1. This suggests that the main influence on the behavior of the SPECI sensor was the daily variation on relative humidity, and that long-term slower fluctuations did not affect the sensor response. Moving on to the analysis of the results with mobile nodes, we observed that from both maps that the absolute concentration of the SPECI DGS-CO sensor used for mobile monitoring was higher than that of the sniffer 4D. Our next slide compares the concentration levels recorded by the mobile nodes on streets, on the left, and to the right, those recorded in residential areas. As can be seen, neither our prototype nor the sniffer registered significant variations in the median, although higher values and greater dispersion were found in the readings taken on streets. Despite the visible difference in absolute values between the mobile sensor nodes, their behavior seems similar, with higher values and bigger dispersion on streets than on residential areas. The comparison between weekdays and weekends wasn't so consistent. Higher values were observed during weekends than during weekdays, which doesn't match the expected behavior, and the median remained practically constant. The clearest differentiation was observed in the traffic intensity variation during the day. Higher concentrations were obtained during rush hours, but since rush hours correspond to sunrise and sunset when relative humidity increases, and based on our previous analysis from the static node, couldn't relative humidity again be the responsible for the increase in the sensor output? In the figure on the right, we observed that both the relative humidity and the output of the SPECI sensor featured higher values during the rush hours. On the other hand, the median value of the sniffer 4D didn't show a significant difference between rush and quiet hours. This leads us to suppose that the increase in the output of the SPECI sensor was indeed due to the increase in relative humidity and not on carbon monoxide concentration. In conclusion, we observed that the responses from AlphaSense and SPECI sensors were not correlated. The AlphaSense CO-before sensor detected higher concentrations during rush hours, which wasn't the case for the SPECI sensor. The daily variation on relative humidity was the main driver for the responses of the SPECI sensors, which at the same time showed a low correlation to low-term variation of relative humidity. The AlphaSense CO-before sensor, on the other hand, showed a very low correlation to relative humidity. Compared to the responses from the AlphaSense sensor in the static node, the SPECI sensor didn't register similar daily nor weekly behaviors, which leads us to conclude that its output wasn't sensible to the ambient air CO concentration level to which it was exposed. Regarding the mobile node, no considerable difference was perceived between readings taken on different areas or days of the weeks. The sensor showed higher values in rush hours, but this could have been influenced by the relative humidity. The air sensor systems developed are still in its prototype phase and require further enhancement and assessment, especially what regards to laboratory calibrations, in-field collocation with regulatory monitoring stations, and long-term performance. These platforms have the potential for increasing the spatial and temporal resolution of monitoring networks in our city, as well as opening the way to new monitoring services and applications. Thank you very much for your attention. I hope you have enjoyed this presentation, and I am looking forward to hearing your questions and suggestions.